This is practice midterm 3, problems 30 through 35, and this series of problems requires you to indicate the orbital hybridization of the central atom in the following molecules as. Now, in this case, like in the previous group, I'm going to, the strategy we're going to employ is the same one we employed with problems 22 through 29. You will have already worked out on your scratch paper, you will have drawn the proper Lewis dot structures with the proper geometry of all of these molecules. And the ones you see here with the asterisk are the ones that I detailed how to accommodate the charge when doing the Lewis dot structures. And so if you have any questions about that, refer to problems 22 through 29. But you will have already done this and used this on that previous set. So now let's go to the problem at hand. We've got to indicate the orbital hybridization, and our options are A, sp, B, sp2, C, sp3, D, sp3d, and E, sp3d2. Okay? And this is going to be contingent upon the E-pair geometry, which we determined on the previous question. And so, for problem number 30, I have beryllium dichloride. We can go look, just to refresh your mind, go back and look at the beryllium dichloride. It's a linear E-pair geometry. It's a linear molecule, but a linear E-pair geometry exists with the beryllium dichloride. Linear E-pair geometry requires that there is sp hybridization on the central atom. And so, question number 31 is the perchlorate ion. We have it, again, depicted up here on our scratch paper. You can see that it has a tetrahedral E-pair geometry. And so, as we determined on the previous question, and by the way, on number 30, it's not SP, it's A, which is the SP option. So let me fix that right now. On 31, we have the tetrahedral E-pair geometry, and that is option C. And with 32, I've got the sulfur trioxide molecule, which we can see one of the resonance forms of on our scratch paper. And it has a trigonal planar E-pair, trigonal planar molecular geometry, and we already discovered a trigonal planar E-pair geometry as well. So that is going to require sp2 hybridization, which is option B. And so real quickly, let's review this. A linear E-pair geometry is going to give you sp hybridization. Trigonal planar E-pair geometry is going to give you require sp2 hybridization. A tetrahedral E-pair geometry is going to demand sp3 hybridization, orbital hybridization. A trigonal bipyramidal E-pair geometry with 5 E-pairs is going to require sp3d orbital hybridization. And option E, octahedral E-pair geometry, 6 E-pairs associated with central atom, is going to require sp3d2 orbital hybridization. So these are all the options that we have for all of these molecules. So now we're to number 33, which is the chlorite ion, which we can see from the our scratch paper. We have 4 E-pairs associated with the central atom, 2 of them lone pairs, 2 of them bonding pairs. 4 E-pairs requires tetrahedral E-pair geometry, and that requires in turn sp3, which is option C. That's the bubble we fill in on our Scantron. Number 34 is antimony pentafluoride. This we have depicted on our scratch paper. We can see there are 5 single bonds associated with the central atoms. So 5 bonding pairs associated with the central atom. 5 E pairs requires trigonal bipyramidal disposition of those E pairs. And so that in turn requires sp3d orbital hybridization, which is option D. And the last, number 35, the tellurium hexafluoride. Tellurium hexafluoride we've already drawn on our scratch paper. It is, there are 6 bonds from the central atom, single bonds to fluorine atoms, and no lone pairs on the central atom. Therefore, 6 E pairs demands an octahedral arrangement of E pairs, an octahedral geometry, and that requires sp3d2, which is option E, which completes questions 30 through 35.